Today I will lead the Sambas to designs a UVM virtual sequencer and virtual sequences. The authors are Clifford Cummings and Johnny Bergeron. Both are very famous. They are first from the abstraction. This paper will clarify important concepts and usage techniques related to the virtual sequencers and virtual sequences that are not well documented in existing UVM reference materials. This paper will also details in the M sequencer and P sequencer handles and the macros and methods that are used with these handles. The objective of this paper is to simplify the understanding of virtual sequencer, virtual sequences, and how they work. This is table of content, table of figures, table of examples. Introduction. What are the virtual sequencers and the virtual sequencers and the virtual sequences, and when should they be used? Tests that require coordinated generation of stimulus using multiple driving agents need to use virtual sequences. This paper will clarify the important concept and usage techniques related to virtual sequencers and virtual sequences that are not well documented in the existing UVM reference materials. This paper will also detail its M sequencer and P sequencer handlers and the macros and methods that are used with these handlers. The objective of this paper is to simplify the understanding of virtual sequencers, virtual sequences, and how they work. When you need a virtual sequencer, Figure 1 shows when virtual sequencers are required. In Figure 1, when is when is the virtual sequencer required? As you see in this picture, in this figure shows the three cases: single driving agent and and multiple driving agent and no stimulus coordinate required, and multiple driving agent stimulus coordinate is required. Therefore, the last two cases we don't need to any virtual sequences required, but in the right driving agent we need a virtual sequencer required, like here. If you have only If you only have a single driving agent, you don't need a virtual sequencer. If you have multiple driving agent but no stimulus coordinating required, you don't need a virtual sequencer. If you have multiple driving agent and stimulus coordination is required, you need a virtual sequencer. It should be noted that if a test bench with a multiple agent and no coordinated stimulus is ever extended in the future to require coordinated stimulus, then the environment will require the update to include one or more virtual sequencers. Those updates, performed later in the project, could be quite painful as opposed to building in a virtual sequencer from beginning and taking advantage of the virtual sequencer when needed. Engineers might want to make a habit of adding the virtual sequencer in most of their UVM test benches. Why virtual sequencer and sequence? System Verilog has a virtual classes, a virtual method, and virtual interface, and all three require the virtual keyword. UVM has a virtual sequencer and virtual sequences, but neither one requires a virtual keyword. There are no UVM virtual sequencer or UVM virtual sequence base classes in UVM. All sequencers and virtual sequencers are derivative of the UVM sequencer class and all sequences and virtual sequences are derivative of UVM sequence class. So, why are virtual sequencers and virtual sequences virtual? Three attributes of virtual sequencers are it controls other sequencers. It is not attached to a driver. It does not process items itself. So, a virtual sequencer is not connected to a driver. Instead of executing the individual sequence items on a driver via sequencer port, it executes subsequences and sequence items on sequencers via handlers to sub-sequencer targets. The UVM user guide sometimes refers to the virtual sequencers as a driver sequencer. A virtual sequencer is a virtual because typically an engineer is not really running sequences on the sequencer. The sequences are being learned on the subsequencer via handlers defined in the virtual sequencer. A virtual sequencer can learn multiple transaction types on multiple real sequencers. The virtual sequence is typically just coordinating executing of the other sequences on the appropriate subsequencers. Three virtual sequencer modes. The UVM user guide describes three ways a user can use virtual sequences to interact with the sequencers. 1. Business as usual, also known as parallel traffic generation. 2. Disable subsequencers. And 3. Use grab and ungrab. The UVM user guide claims that most users disable the subsequencers and invoke sequences only from the virtual sequence. But our experience and the experience of many verification engineer colleagues is that the most popular virtual sequencer mode is parallel traffic generation, also known as business as usual. This is the mode that is described in this paper. 6. How are virtual sequencers implemented? A virtual sequencer is little more than a component to drive a locus and scope to configure virtual sequences and provide handlers to the sequencers that will be required by virtual sequences. The code for a virtual sequencer is rather simple. The subsequencer handlers declared in the virtual sequencer will be specified by the configuration database after all components are built, after the build phase, and are typically set by the environment in the connect phase. Consider the virtual sequencer code example 1. The example 1, simple virtual sequencer code. Class V sequence extended with UVM sequencer, and it has the sequencer and construction and end of elaboration phase. It check the sequencer specified. Example 1 is a typical structure for a virtual sequencer, and the usual selected name for this example is V-sequencer. Virtual sequencers are extended from the V-sequencer, not UVM virtual sequencer, which does not exist. Unlike a normal sequencer, the virtual sequencer of example 1 is not super usual parameterized to a transition type because this sequencer will be able to execute multiple transition types. Extending a virtual sequencer from the UVM sequencer base class without any parameters means that the virtual sequencer will use the default parameterized values of UVM sequence type, sequence item. The virtual sequencer declares The virtual sequencer declares subsequencer handlers. In example 1, the subsequencer handlers are called AHB sequencer and Ethernet sequencer ETH respectively. These two subsequencer handlers will be assigned from values specified in the configuration database during the end of elaboration phase. Unlike transaction level modeling, a model (TLM) connections that are used to connect the most components in a UVM test bench, the subsequencer handlers set not set using a TLM connect method, but are specified by the environment using the configuration database. It is then the job of the virtual sequencer to extract those handlers from the configuration database and assign them to the two handlers declared in the virtual sequencer. The actual subsequencers will be created in the build phase. Therefore, their handlers will only be available to be put in the configuration database by the environment in each connect phase. Thus, the virtual sequencer will have to retrieve them in the next phase, end of elaboration phase. Finally, the vSequencer example includes in the typical new construct is the command to all UVM components. It can be seen from this example that the virtual sequencer is just a container for handlers to subsequencer and other configuration parameters. The virtual sequences assume the virtual sequencer has been properly configured before the virtual sequence is executed in the long phase. They can then access these configuration parameters in the virtual sequencer via their p-sequencer handler. 6.1 Simplified virtual sequencer implementation. The authors have also used a simplified version of virtual sequencer. The simplified version does not retrieve the self-sequencer handlers from the UVM config DB, and therefore does not need the end-of elaboration phase method. In the simplified version of the vSequencer, shown in example 2, the subsequencer handlers are still declared, but instead of virtual sequencer retrieving the handlers from the UVM config DB, it will be the job of the environment to copy the subsequencer handlers from the initiated agent to the handlers declared in this vSequencer. Example 2, simplified virtual sequencer code. It has the virtual vSequencer, a vSequencer class extended from the UVM sequencer, and there is a sequencer declaration and definition, and there's no other things except the construct. The EMV used with the simplified vSequencer is shown in section 17.1. The vSequencer of example 1 has the advantage that it extracts its subsequencer handlers that will be stored in the UVM config DB, which might make the example 1 vSequencer easier to reuse the different hierarchies, while the vSequencer in example 2 is indeed simpler and it is not difficult for the environment to copy the subsequencer handlers directly into the simple vSequencer. Cliff typically uses the simplified version of the vSequencer and avoid the additional and of elaboration method phrase method. 7. Sequence details. Sequences are run on a sequencer and are parameterized to the transaction time that is processed by that sequencer. Sequences started on a sequencer using the built-in sequence start method or by using the UVM underscore do macros. Every sequence has a handler to the sequencer that is running that sequence. That handler is called the mSequencer handler. What is the sequencer handler? All sequences started on a sequencer pr underscore uh, seq dot start env v sequencer env dot vsqr. The UVM do macros also execute this command. After starting a sequence on a sequencer, the mSequencer handler for the sub sequence is set to env.vsqr. The mSequencer handle is just a handle in every sequence that points to the sequencer that is running the sequence, and it was set when the start method was passed to the handler of the sequencer, env.vsqr in this case. Just like any other sequence, when a virtual sequence is started on a virtual sequencer using either start method or the UVM macros, the virtual sequence will automatically have an mSequencer handle that correct point to the virtual sequencer. 9. What is the p-sequencer handler? Frequently asked questions include: what is a p-sequencer? How is the p-sequencer different from m-sequencer? All sequences have an m-sequencer handler, but sequences does not automatically have a p-sequencer handler. Furthermore, the mSequencer handler variable, the the mSequencer variable is an internal implementation variable that is poorly documented and should not be directly by the verification engineers. It is an artifact of the system Verilog language, which lacks a CTOR plus concept of friend classes that is variable that this variable is public. Any variables or the method with the m prefix should, similarly, not be used directly. The p-sequencer is not automatically declared and set, but can be declared and set by the using UVM declare p-sequencer macro. And as will be shown later in this paper, the UVM declared p-sequencer macro and p-sequencer handlers are user conveniences. Technically, the p-sequencer handle is never required, but when used with the UVM declare p-sequencer macro, it is automatically declared and set and checked a virtual set when a virtual sequence is started. Properly points to the virtual sequencer that is running the virtual sequence. More about the p-sequencer handler and its usage is described below. Okay, the section 10. What is the UVM declared p-sequencer macro? The UVM declared sequencer macro code is defined in the source macros sequence defined as VH file and is a rather simple code. This macro has a sequencer and p-sequencer, and virtually the method is like here. Yes. What is the p-sequencer is? I'm not sure what it is exactly. What does it mean? What does this definition mean? The UVM declare p-sequencer macro executed to useful steps. 1. Macro declares a p-sequencer handler of the sequencer type. The macro then casts the sequencer handler to the psequencer handler and checks to make sure the sequencer executing the sequence is of appropriate type. A closure look at this macro and what it does is instructive. This macro is typically placed in a sequence-based class that will be extended to create all of the sequences that use the designated sequencer, virtual or not. On line 1, the user calls this macro and passes the type of the sequencer that will be used by the sequences. For virtual sequences, this is the class name of the designated virtual sequencer they will execute on. On line 2, the designated sequencer is declared with the handle name psequencer. For the remainder of the code in this macro and everywhere else in the user-defined virtual sequence space and extended virtual sequence classes, the virtual sequencer will be referenced by the name psequencer. From this point forward, there is no need to reference the name of the virtual sequencer that is being used. The user can simply reference the psequencer virtual sequencer handle. This is simply a convenience, not a requirement. On line 3, the start of the virtual void function declares the continues through the line 9. The void function is called mSet and this function is called whenever a sequence start method is called on a virtual sequences or a UVM do on macro is used to start the virtual sequence. Line 4 ensures that if the virtual sequence is extension of another virtual sequence, the base virtual sequence will execute its own mSetPsequencer method. Line 5 casts the internal mSequencer handler, which should be handle of a virtual sequencer to the local psequencer handler declared on line 2. The if test checks to see if the cast operation failed, and if the cast did fail, the failure message on line 6 to 8 will terminate the UVM simulation and report the consistency message that there was a problem casting to the specified virtual sequencer type, that is, the sequence is executing the on a sequencer and the wrong type. So the if test and cast operation and corresponding constants error messages are also shown in figure 3. The figure 3 UVM declare psequencer cast m sequencer to a psequencer. Note: if the sformat command is a one long string on one line of code, line 7 and 7-8 in the macro, the 11 example virtual sequencer test bench. Trying to describe the virtual sequencer test bench construction operation without a block diagram requires a great deal of concentration on the part of the reader. So, example files to run virtual sequences on a virtual sequencer test bench of figure 4 will be described in this paper. Any files required to run this simulation that are not described in the body of this paper have been added to Appendix 2 at the end of this paper. Figure 4, example sequencer and the block diagram. The sequence block diagram. The virtual sequencer of this test bench was shown in example 1, or other test bench files will be described in the remainder of this paper. Okay, 12. Virtual sequence base classes. All virtual sequences need access to the subsequence handler defined in the virtual sequencer. To gain access to the subsequencer handler, the virtual sequences need to use UVM declare the p-sequencer macro to declare and set the p-sequencer variable the subsequencer handlers are readily accessible. Since every virtual sequence needs to execute these steps, it is recommended to put this code into virtual sequence base class via sequence underscore base, and then create all virtual sequences by extending the vSequence base class. Okay, 13. Example vSequence base. For the virtual sequencer shown in example 1, we can use the vSequence base definition shown in example 3. In example 3, the class of vSequence base extends the UVM sequence, and it has a UVM declared p-sequencer and the constructor and their sequencer definition, and there is a body task. Example 3. This is the example 3 virtual sequence base class example called vSequence base. The vSequence-based class uses a UVM declare psequencer vSequencer macro to declare the psequencer handle of the vSequencer type. The vSequencer base then declares the AHV sequencer and the ETH sequencer handles of the same types that were declared the virtual sequencer shown in the example 1. The vSequencer base then copies the virtual sequencer psequencer AHB sequencer and ETH sequencer handles to the local AHB sequencer and the ETH sequencer handles. The vSequencer base class used the psequencer handlers, which should have been properly assigned to the UVM declared psequencer macro. To copy the handlers from the virtual sequencers and the virtual sequence base class. Using the UVM declared psequencer macro, and it was not necessary for the vSequence base class to check the type of the vSequencer class since the macro set up a void function to perform the check. Note that the vSequence base class assumes that the handlers were already set in the virtual sequencer. It is job of the environment to ensure the subsequencer handlers are properly set. 14. Creating a virtual sequences. Once the virtual sequence base class has been created, it is possible to create a virtual sequences that are an extension of the virtual sequence base class. Every virtual sequence that is extended from the virtual base class inherited the subsequencer handles of the correct type and already properly assigned. Consider the two virtual sequences example shown in the figure 4 and example 4 and example 5. These sequences are example of the virtual sequences that are extension of the virtual sequence shown in figure shown in example 3. There are two accepted methods for executing a sequence in the UVM. First one is the UVM do macro, which are generally considered to be the easiest to use but may also be less simulation efficient because the subsequences are always allocated and randomized before being executed. More difficult to understand if the user ever extended the UVM macro code. The second is the use explicit allocation and the dialect assignment or the calls to randomize for the start method to execute the sequences on the chosen subsequencer, which is generally considered to require more using code for effort, but the straightforward and or allow the creation and execution of more directed sequences. The example for virtual sequences use the UVM macro to run a virtual sequence to randomly generate pseudo AHV packets followed by the two sequences of pseudo Ethernet packets and concludes with another sequence of pseudo AHV packets. The code for the pseudo Ethernet and the AHV transactions along with the Ethernet and the AHV sequences, and then test that run the v sequence v c underscore seq 1 will be shown later. Okay, in the example 4, v sequence to 1 extend the front of v sequence space uses UVM do on macros. As you see, class v UVM sequence extend the v sequence underscore base and the constructor, and in the body task, uh, it has some sequence sequences, and then it called from like this UVM info and do UVM do on and the sequence packet, event packet, and the AHM sequence. That is a sequence. The package is just a sequence, and there is a sequencer. And the example 4, virtual sequences uses calls to the randomize and the start method to run a virtual sequence and randomly generate a pseudo AHV package followed by two sequences of the pseudo Ethernet package and conclude with another sequences of a pseudo AHV packet. The code for the pseudo Ethernet and AHV package, along with the Ethernet and AHV sequences, the test that runs the v underscore seq2 will be shown later. Class v sequence to extend the v sequence base and the constructor and in the body. In the body, it is created by the creators that the sequences are created through the factory, and there is in this is the calling the super body, and there is randomized and start. Okay, like this. This is the example 5 v6 seq2 extended from the v sequence space and uses a sequence randomized and sequence start method. Okay, 15. Calling sequences from a virtual sequences. Okay, this now we can start to the direct exploration from the virtual sequences. One important feature of the virtual sequences is that they can run the existing sequences without modification. The user can create a library of sequences that are used to test individual subblocks, and then use the same sequences and coordinated virtual sequences to test multiple subblocks using the original subblock sequence libraries. There is no need to recode or modify the subblock sequences. Okay. Consider the pseudo AHP packet code shown in example 6. This is a pseudo AHP packet because it only contains two non-standard AHP fields, and an example DUT will recognize when these fields have been sent to the DUT and print the information to screen of the examination. That's example 6, AHV packet, pseudo AHV packet code. This AHV packet extends the UVM sequence items, and this item has only address and data because it is a pseudo, and there is a function cover to the string, only this function. This class is extend the UVM sequence item. Consider AHV sequence code shown in figure 7. 7. This simple AHV sequence randomly generated 225 AHV package. The virtual sequences in the example 4 and 5 send this random generated set of the AHV package and the AHV SQL handler declared in the vSequencer component. AHV sequence extend the UVM sequence AHV underscore packet and land in constraint C1. There's a new, there's body. In this body, it's just a repeat CNT, like here. The user 7 AHB SCQ1 AHB sequence coded by a virtual sequences. Consider pseudo Ethernet packet code shown Example 8. This is a pseudo Ethernet packet because it only contains two unknown standard Ethernet field and the example DUT and recognize when these fields have been sent to the DUT and print the information to the screen for examination. Example 8. ETH underscore PKTSV pseudo Ethernet packet code is very similar to the AHB packet. Consider the Ethernet sequence code shown in example 9. This simple Ethernet sequence randomly generates 2 to 4 Ethernet packets. The virtual sequences in example 4 and example 5. Then this randomly generated set of the Ethernet packet to the Ethernet sequencer handler declared in the vSequencer component. Class ETH underscore SQ1 extend the UVM sequences. And there are some around and the constraint and the constructor and the body task. I created a ETH packet 1 and there is a repeat and a start item and a finish item and there are some randomized. This is the sequence. Even a sequence code by the virtual sequences. Okay, now 16. Starting virtual sequences. In general, virtual sequences are generated from a test using the sequence start method. The UVM do on macro cannot be called from the test component. The UVM do on macro is only called from the derivative of the sequences. This was a bit tricky to determine. This was a bit tricky to determine, but even if a UVM do on is called from a test on a valid virtual sequencer handler, the UVM do on macro calls methods that are defined in the sub UVM sequence space class located in the UVM source, UVM, SRC, SC2, UVM sequence base SVH file. The required message create item, start item, finish item, and none of these methods are available in the UVM test base class and any other UVM component class or derivative. It is a good idea. It is a good idea to create a test base class with a common declaration and a method that will be used by every other test in the verification suite. The test-base class is shown in Figure 10. Declare in the environment to handle the create environment in the build phase. These actions will not be these actions will not need to be repeated in the test and extended the test class that extended this test base class. This test base also includes the start of simulation phase to print a test structure and a factory content before the simulation executes in the long phase. It is useful to print the test bench structure and the factory content in the start of the simulation phase, because the trouble most often appear in the long phase, so these pre-run printouts can help diagnose if any components were incorrectly constructed or if some of the test bench classes were omitted from the factory. Here, example 10, test underscore base. The carrier is built in the environment printed the test bench structure. Test base extend the UVM test. And there is E. This is test E. And the function test, the string. This is constructor. And this is the phase, build phase. And this is start of simulation phase. Now, once a test base class is coded, each of the tests can be extended test space and create individual tests. Example 11 shows the test 1 class definition and extended from the test base class. The test 1 class example defines the long phase for this test, which declares the first virtual sequence v underscore 1, v underscore seq1, and handle the v seq and create a v seq object. This test then calls the range objection method, printing methods, calls the start method, and a VSEQ sequence, and it passes the inbound virtual sequencer path e.v_sqr to the start method. Once the virtual sequence has completed, the test prints one or methods is the called drop objection method and finished. The example 11, test 1 SV declares the v-sequence handler and calls v-sequence start e.v_sqr. This test 1 extends the test base and found there is a constructor and the long phase. In the long phase, there are some like a lazy objection and drop objection. The test2.sv declared the VQ sequence as a handles codes here like there, and there is class the test2 code in example 12 does the same thing in the test1 code of the example 1, except that the test2 code declared the SEQ handler to be the second virtual sequence type v_SEQ2. 17. The environment set to the handlers in the virtual sequencer. The environment code shown in the figure 13, example 13, is pretty typical environment code with the exceptions that it declares the virtual sequencer handler v-sequencer v_sqr, builds the virtual sequencer and stores the Ethernet ETH_AGNT and the AHB AGNT sequencer handlers SQR and SQR in the configuration database. As was discussed in the section, how are virtual sequencers implemented? The virtual sequencer handlers are stored in the configuration database by the environment in the connect phase for the retrieval by the sub-virtual sequencer in the end of the elaboration phases as opposed to the using TLM connections that connect most test bench components. The example 13 shows the ENV-SV environment with the virtual sequencer. Class ENV extend the UVM ENV like here TBETH agent and the agent ETH agent and AHB agent and declared and definition, and the V sequencer is v_sqr is declared defined. And there is there's a constructor, and in the build page, as you say, agent 2, agent 2, and agent are created, and the SQR, the V sequencer also is created, and then those are the the sequencers that are set in this sequencers are stored in the config db using the set method. The 17.1 Simplified Environment Implementation. The author have also used a simplified version of virtual sequencer as described in section 6.1. The simplified version does not retrieve the sequencer handler from the UVM config db and therefore does not need to the end of the elaboration phase code. In the simplified version of the sequencer shown in the example 2, the subsequencer handlers are still declared, but instead of a virtual sequencer retrieving the handlers from the UVM config db, the environment copies from subsequencer handler from the instantiated agent to the handlers declared in the v-sequencer as shown in the connect phase of the environment shown in the example 14. The code, the ENV, example 14, ENVSV simplified the environment code. And the code, we can see the ENV extend the UVM, and there is the agent are defined, and there is the sequencer, constructor, and in the build phase, the And there are created the agent and sequencer, and then connect phase. We can connect the V sequencer and the AHV, the sequencer connected to the sequencer. We can assign. Cliff typically use the simplified version of the V sequencer and the EMV to avoid adding the additional and of the elaboration phase method to the V sequencer. Now next is the M18 M sequencer handle create details. For those readers who want to know details about how the M sequencer handler is created inside of UVM, see Appendix 1. The 19th summary. This paper describes the necessary steps to create an working virtual sequencer environment and explained the purpose of M-sequencer and P-sequencer handlers and the UVM declared P-sequencer macro. These are topics that are often confusing to new and experienced UVM verification engineers. This paper also includes all code of necessary to the test example described in this paper. Okay, 20 is the acknowledgement. 21 is errata changes. The okay, and it includes the references and author and connecting information, and it also has some the appendix and the appendix 1 and 2. Okay, hmm, I think I have read all things that I about these papers. Thank you very much. See you next time.